This problem I call easy as falling off a log. The idea is we have a small bead on the top of a cylinder, or it could be a sphere for that matter, and it slides frictionlessly on the cylinder, and it's at rest and is given the tiniest of nudges, and it starts sliding down the surface of the cylinder. As it goes down, as potential energy gets converted to kinetic energy, the bead goes faster and faster. Eventually, I think you all know what's going to happen. Somewhere, the bead is going to lose contact with the cylinder and become a projectile. And the object of this problem is to find out what theta is. So here's the little bead at some angle theta, and we want to find the value of theta when the bead just comes off of the surface of the cylinder. And so the first thing we ask ourselves is the energy conserved here? And so we have to ask, are there any external forces doing work? All right. So if we look to the right here, I've sort of drawn in a different coordinate system, but I've drawn the little bead when it's at the angle theta, and you see that the angle theta, now you should convince yourself that the angle theta is as I have drawn it here, between my positive x-axis, which points toward the center, okay, and the bead itself. So what are all the forces on it? Well, there's its own weight, mg, but that's not an external force because we're going to introduce a potential energy for it, mgy. And over here we have a normal force, which the cylinder exerts on the bead, and that is an external force. But as in the case of the roller coaster problem, since the normal force is always perpendicular to the direction in which this object is moving, it never does any work. And so the total energy of this system must be conserved. So let's start off and call the initial energy E1. Okay, so I'm going to write here that the initial energy of this system, and this is what it will be ever thereafter, if I choose y equals 0 to be at the center of the cylinder, then it's equal to mgr. And that's what the energy will always be. E2 is equal to 1/2 mv squared plus mg. And now you have to ask yourself what this distance is, okay, because that's the height that the guy is above there. And so you see that this distance is r cosine theta. And so energy conservation then says, see that when we set these equal to each other, okay, this has got to be equal to mgr. And so when you set these equal to each other, you find that 1/2 of v squared is equal to mgr times 1 minus cosine theta. So we end up with one equation with two unknowns, theta, which is the thing we're looking for, and the velocity, which we don't know. Okay, so we need to, in fact, look in a little bit more detail at the dynamics of the problem, and we'll do that by looking at this picture here. Okay. So as this guy is moving with speed v in a circle of radius r, his acceleration is pointing toward the center of the circle, and I've indicated the acceleration as a, pointing in this way, and a, of course, has got to be v squared over r. The other forces, as we've noted already, are mg and n. And of course, I'm going to now choose a coordinate system. Now that I've chosen a body, I'm going to choose a coordinate system in which one axis, I'll call it the positive axis, positive x-axis, increases in the direction in which the acceleration vector points. That means that in the y direction, this guy will have another acceleration, but we're not really interested in that one. Okay, we'll write down the equations and everything, but what we're really interested in is finding out what the velocity is, and we'll be able to find that out just by looking at the sum of the forces in the x direction. So let us proceed now and apply Newton's second law in this coordinate system. And so the sum of the forces in the x direction is equal to the mass of the object times its acceleration, which is v squared over r. That's the radial acceleration or the centripetal acceleration. And that has to be equal to mg times the cosine of theta minus n. So let's have a look at what n is here. Okay. So n is equal to m times v squared it's m times g cosine theta minus v squared over r. So at the very beginning, v is very small, and so n is positive, the way I've drawn it here. As the bead goes faster and faster, the quantity in parentheses here is going to get smaller and smaller until eventually the normal force will be 0. The normal force will be 0 when v squared over r is equal to g cosine theta. Okay? That's the point at which it will leave the surface, because that's how the bead knows that it's on the surface. It feels that normal force. If that normal force disappears, then it's going to move only under the influence of its own weight. In other words, it's going to become a projectile. Okay, so what we have found out here is that v squared is equal to g cosine theta, gr cosine theta. So v squared is equal to r g cosine theta. So we can put this up to here, and we can solve for theta. So let's do some of that algebra. Now I would like to make a confession here. I had an m in here, right here, that shouldn't be there, and I erased it surreptitiously. But you can do the algebra on the original equation. You can see that the m's all cancel out. Okay, so at any rate, we take this, put it in here, and we get 1/2 rg cosine theta equals rg times 1 minus cosine theta. And the r's cancel out, and the g's cancel out. And you see this thing is going to behave exactly the same way with regard to the angle it comes off, no matter what the mass is, no matter what the radius is, no matter whether you do it on the moon or the earth, doesn't depend on anything except the solution of this equation. And let's see if we can solve this equation. And so we have 3/2, so we have cosine of theta is equal to 2/3. And if I pull out my calculator, and I find that this is about 48.2 degrees. That's it.